shape it, or kind of why we're all here, and the source of all of our questions. And the exceptional example of diversity is an adaptive radiation. And some of it's often characterized by key innovations or novel traits that allow organisms to exploit new niches, or diversifying selection that fine-tune these traits to optimize the fitness in these niches. And an exceptional example of this within mammals is the superfamily of bats known as noctilionoids. And this family is well known for its dietary diversity. These guys are eating pretty much everything under the sun. It includes the vampire bats, and in mammals where the vomeronasal organ is vestigial, such as in several aquatic mammals, as well as us humans and other old world primates, TRPC2 is a pseudogene, so it's accumulated mutations where the protein is no longer functional. Now, if we try to understand how the pattern of vomeronasal function has evolved throughout the tree, there are kind of two scenarios which could have occurred. So the most parsimonious scenario is that the ancestor of all bats did not have the vomeronasal organ was absent, and it was regained twice throughout the tree. And this might support that hypothesis that the VNL regain was a key innovation. Alternatively, and far less parsimonious, is the TRPC2 and the vomeronasal organ was functional in the ancestor and subsequently lost after major bat families have diverged, but has retained function in light of all these losses in the few groups that do have it. And this would suggest widespread TRPC2 loss. So I sequenced TRPC2 in over 116 species of bats across over 75% of the species diversity. And we particularly focused our samples in these groups that had a functional vomeronasal organ. So when we compared the sequence in the mouse where we knew the gene was functional, we had, what we found was 13 independent pseudogenizing mutations that have occurred throughout the tree of bats. So this is highlighted in pink here, independent pseudogenizing mutations. This is 3 times less than we've seen in any other mammals. But when we look at the groups that do have a functional vomeronasal organ, the TRPC2 remains intact, as well as in most noctilionoids. A few surprises, such as in this Caribbean nectar-feeding group, an ancestral deletion that has disrupted the protein. But talk to me later about that. So now we have a more clear understanding of the pattern of losses across bats, but this has not actually addressed where the shift in selection has occurred. So to do this, I'm going to use a statistic called omega. And this is calculated for the ratio of non-synonymous to synonymous substitutions. So when omega is, we would expect under strong selection, strong purifying selection, for omega to be close to 0, as non-synonymous mutations might disrupt the protein. However, as selection relaxes, estimates of omega will shift towards the right, towards a more neutral ratio where the two rates are in unity. So we classified the 2 different branch classes, those with a pseudogenizing mutation in all other branches, and saw where the omega estimates fell along the spectrum. And so we simulated TRPC2, we simulated sequences of similar parameters estimated from the TRPC2 data 1,000 times. And there's kind of 2 distributions that we might expect would happen. So if TRPC2 retained function, that means that the branches that were not pseudogenized would be under strong purifying selection compared to the pseudogenized branches. And so we would expect the distributions to be distinct. However, if TRPC2 had reactivated and was evolving neutrally in the ancestor of all bats, then we wouldn't be able to distinguish these estimates of omega from the extant pseudogenized lineages, and we would expect that the estimates of omega distributions would overlap. Indeed, what we found was that not only do we have 2 distinct distributions, but the variances of these estimates from the simulations, as well as from our observed data, are informative. So if we look at the black distribution in the branches where the TRPC2 is functional, the variance is very low, the distribution is very narrow, suggesting that TRPC2 has invariantly been under strong selection since the divergence of all bats. Whereas TRPC2 has relaxed, selection has relaxed at different times, attributing to the wider variance of estimates of omega of this pseudogenized branches, where TRPC2 is pseudogenized. So answering our question, could the Vomeronasal system serve as key innovation? I argue no, because the Vomeronasal organ has always been there since the divergence of, or since the ancestor of all bats. It's just been subsequently lost more recently. Now, have the pheromone detecting receptors, just because there hasn't been a new or regain of Vomeronasal organ doesn't mean that there hasn't been diversifying selection occurring in noctilianoids and their receptors. So we're going to turn to this gene family known as V1Rs, or the Vomeronasal receptors. And these are receptors that bind directly to the pheromone. So this has led to a large diversity in the numbers of the Vomeronasal receptors across mammals. So you can see